Hello everybody, myself Jyoti and this is fourth lecture on Raman spectroscopy. In the last lecture we spoke about we discussed about the polarizability of the molecule, and we know that this polarizability, it is affected by the internal motions of the molecule. When I say internal motions are of two types. One is vibrational motion and other is rotational motion. Vibrational motion in a molecule, it is because atoms are continuously vibrating about their mean position, and rotation of the molecule is like the molecule rotates as a whole. So here we will see what is the effect of vibration on the polarizability of the molecule and what is the effect of rotation on the polarizability of the molecule. Now, the nuclei in a molecule vibrate about their mean position, and this causes the polarization of the molecule to change continuously. Now, suppose alpha 0, it is the equilibrium polarizability of the molecule, and alpha is the changing polarizability, or you can say instantaneous polarizability of the molecule at a particular time instant. So, we can write alpha. This looks like A, but it is alpha uh, because of some font. So alpha is equals to alpha 0 plus beta sine 2 pi nu t. This nu t here is the vibrational frequency. Nu, we know that it is a vibrational quantum number. Frequency, we generally use the symbol nu. So nu and suffix nu. So it is the vibrational frequency, and beta, it is a measure of change of polarizability. Now, the induced dipole moment mu is, we know that mu, it is alpha E. What is mu? Mu is the induced dipole moment. So we know that when we apply a static electric field to the molecule, then there is a electric dipole moment which is induced in the molecule, which we represent by letter mu. So that is this mu. So induced dipole moment mu, it is given by alpha E. We will substitute the value of alpha. Alpha is alpha 0 plus beta sine 2 pi nu t, and E, suppose it is E0 sine 2 pi nu t. Here E, the electric field, we are considering as a changing electric field, oscillating electric field. So suppose E, it is E0 sine 2 pi nu t, that is oscillating electric field. Now when we are considering oscillating electric field, the dipole moment is also oscillatory in nature. So mu, it is given by this sine 2 pi nu t, so that is also oscillatory in nature. So if I solve this bracket, alpha 0 E0 sine 2 pi nu t plus beta sine 2 pi nu t sine 2 pi nu t, and then I use the formula sin A sin B equals to 1 by 2 cos A minus B plus cos A plus B. When I use that formula, I will get alpha 0 E0 sine 2 pi nu t, that is this term when I multiplied, and half beta E0 cos 2 pi. I have taken 2 pi common. 2 pi nu t minus half beta E0 cos nu plus nu t. Because I have used here sin A sin B. I have used the formula sin A sin B equals to 1 by 2 cos A minus B plus plus half cos A plus B. That formula I have used over here. Now, if you will look at this equation of mu carefully, you will observe three terms. This is first term, this is second term, and this is third term. So I can write mu in the form of components of a moment. So mu1, mu2, mu3, where mu1, it is equals to alpha 0 E0 sine 2 pi nu t. Mu2, it is equals to half beta E0 cos 2 pi nu minus nu t. And mu3, it is minus half beta E0 cos 2 pi nu plus nu t. So the above equation, that is mu equals to mu1 plus mu2 plus mu3, it shows that mu consists of three components, and all these functions are oscillatory functions, but their frequencies are different. Hence three lines are obtained corresponding to three different frequencies. So here, what are the frequencies? See, for mu1 the frequency is nu. For just a second. For mu2, the frequency is nu minus nu. And for mu3, the frequency is nu plus nu. So we are observing three frequencies. One which is nu, another which is nu minus nu, and third one which is nu plus nu. So the perturbed lines, that means the lines whose frequencies change. One is nu minus nu, another is nu plus nu. These perturbed lines are symmetrically placed about the unperturbed line, that is nu. and the former being Stokes line, because we know that for the Stokes line frequency is less and for the anti-Stokes line frequency is more. So naturally nu minus nu corresponds to Stokes line, nu plus nu corresponds to anti-Stokes line. Now, if we assume that if the internal motion or vibration of the nuclei in a molecule did not exist, then the vibrational frequency would be zero, and hence mu2 plus mu3 would be zero. And if mu2 plus mu3 would be zero, we will not get any perturbed lines, any Raman lines, and then we cannot observe Raman effect. And so same could be said about the situation in which internal vibrations existed but did not affect the polarizability. In some case, what can happen that there are internal motions, but those internal motions are not affecting polarizability. They are not changing polarizability. We know that the condition for to observe Raman spectra is there should be change in polarizability of the molecule. If there is no change in the polarizability of the molecule, we will not get Raman spectra. Now, in order to be Raman active, internal motions in a molecule, that is whether you are considering vibrational motion or rotational motion, they should cause some change in polarizability of the molecule. Like we have studied vibrational spectra and rotational spectra. We can observe vibrational spectra and rotational spectra only when there is a changing dipole moment associated with it. In case of Raman spectra, we can observe Raman spectra only when there is a change in the polarizability of the molecule. And this change in polarizability, it can be in magnitude or in direction or both. Now this was about the effect of vibration. Now let us come to effect of rotation. Now when we say that a diatomic molecule it is rotating, the orientation of the molecule varies with respect to the electric field of radiation, and if a molecule is not optically isotropic, it exhibits different polarizabilities in different directions, and then its polarizability will vary with time periodically with frequencies equal to twice the frequency of rotation. In case of vibrational, it is changing with the frequency of vibration, but here the polarizability is varying. When we consider rotational motion, polarizability will vary with time periodically with frequencies equal to twice the frequency of rotation, and hence when we write the equation for this, we will have to write 2 nu r. वहां पे हम लोगों ने इक्वेशन क्या लिखा था फॉर दी वाइब्रेशन, अल्फा इक्वल्स टू अल्फा जीरो बीटा साइन 2 पाई न्यू न्यू टी. Nu is the vibrational frequency. Here we are writing, instead of nu we are writing 2 nu r because the change is happening twice. So 2 nu r into t, where nu r is the rotational frequency. And here beta dash is a measure of change of polarizability due to rotation of the molecule. Beta was because of the vibration, beta dash is because of the rotational motion. Now, during end-over-end rotation, the ellipsoid presents the same appearance to an observer twice in every one complete rotation, and that is how we take the frequency as 2 nu r. So, rotation by rotational motion will bring a diatomic molecule in a position in which its polarization is same as initially, and hence the rate at which the polarization changes is twice as great as that of the rotation. Now again we will consider the induced dipole moment, that is mu. Mu, it is given by alpha E. We will substitute the value of alpha. We will substitute the value of oscillating electric field E. So we know that alpha E is alpha 0 plus beta dash sine 2 pi 2 nu r t. E is E0 sine 2 pi nu t. Then again sine A, sine B. So I will substitute the formula sine 1 by 2 cos A minus B minus half cos A plus B. So this is alpha 0 into E0 sine 2 pi nu t, that is first term, and beta dash common, E0 common, and here I can write cos A minus B 2 pi nu minus 2 nu rt minus half beta E0 cos 2 pi nu plus 2 nu rt. Here I have considered this as A and this as B. Okay, keep that in mind. So again we can write this equation in terms of three components. Mu is equals to mu1 plus mu2 plus mu3, and The equation shows that again mu consists of three components. All are oscillatory functions, but their frequencies are different. So the frequencies are, इसका frequency है mu1 का nu, frequency of mu2 is minus nu minus 2 nu r, and frequency of mu3 is nu plus 2 nu r. So where nu minus 2 nu r and nu plus 2 nu r, they are symmetrically placed as they are the Raman lines, one being Stokes line and another being anti-Stokes line. So here we can know that if the molecule is not rotating, then there will not be change in the polarizability of the molecule because of the rotational motion, and in that case we cannot observe Raman spectra. So Raman spectra we can observe only if there is an internal motion. Intermotional in the sense there should be vibration, there should be rotation, and there should be rotation and vibration in such a way that they cause some change in the polarizability of the molecule. Then only we can observe Raman spectra. So thank you so much.